Thank you very much for inviting me, and it's a delight to be the very first speaker of this SMALP membrane protein meeting. I'm very honoured that you've allowed me to speak. So today I'm going to quickly run through a little intro about the HexAuFoil grids. But first, perhaps appropriately, because I'm the first speaker, a little bit of history. So when we started doing cryo-EM, we had, just to remind everybody, the traditional CEM grid was in use, was a metal mesh with a 10 nanometer thick carbon film. And the Quantifoil, the original thing about Quantifoil, why we're called Quantifoil, is that we were able to produce holes with predetermined size and arrangement in a wide variety of patterns. And that was really what was used from when they were invented in 1999 for at least 15 years and was the standard grid type. The problem with these, as was shown by Chris Russo from LMB, is that as you freeze things with the differential effects, freezing effects of carbon and metal, and also water and metal and carbon, you get strain introduced into the system, which is released when you locally heat the sample. And this is a major contributor to beam-induced motion, which is a major part of the motion that you see when you first expose your sample to radiation. And so you lose your least radiation damaged data due to the effects of this of the differential motion between your carbon film and your metal grid. As I think everybody knows, about 10 years ago now, Chris initially came up with one solution to this problem, which was that you simply made the film out of gold. And that was commercialized by us as HexAuFoil, and that eliminates this differential contraction of carbon and metal, and has been shown quite extensively, perhaps best by Rado Denev about 3 or 4 years ago, that you do gain about half an angstrom of resolution just from this simple, not so simple, moving from carbon film to gold film. Okay. So solve the problem. So now we've addressed the motion of the samples within the plane of the grid, because you don't get carbon film crinkling due to a differential contraction of the metal and the gold of the carbon. However, the ice also expands differently from the metal, and you get a compressive strain that causes the grids to kind of buckle upwards. You can think of it as a bit like kind of a trampoline. When you press weight on, it goes up and down, and you hit it with the energy, and you get this strain released, and you get a motion almost kind of perpendicular to the grid. Chris was able to show that that this buckling occurs if your grid is more than, if the width of your grid is more than 11 times the thickness of the ice that you want to get. So 30 to 40 nanometers of thickness of ice, you need holes that must be smaller than about 0.3 micrometer. And he showed this very nicely with some tilted data where you get very much more movement in the perpendicular to the grid. So this is a tilted and this is planar as you go up in hole size. Okay, so there's a small problem with that, which is when you make a HexAuFoil or an HexAuFoil, the process is done by floating a pattern film onto a grid that's brought in. Now, that leads to a smallest hole size of 0.6 micrometer and a variation in hole size. So this is whenever you're using any carbon grid or HexAuFoil of plus or minus 0.2 micrometer. So we're trying to get to a hole of 0.3 micrometer, and our variation in hole size is almost that big anyway. So Chris didn't give up. He invented a completely new way to make grids. And this really is going to be the heart of my talk here. This completely new way to make grids so that we can get to this 0.3 micrometer hole size involves now making grids as a single unit. We start by doing a process of lithography from a pristine wafer, a lithography process and cryo-evaporation of gold to form at a wafer scale your film. But the film is now patterned so that it's got you've got 1,000 grids, grids worth of film patterned with the shape of the individual grids on it. And then we do another piece of lithography onto that film to make the grid. And then we release those grids from that wafer and pack them, and this becomes more. But the beauty of this cryolithography, then lithography, gives us really great control over what your grid looks like. We can go down to holes as small as we're needed, but even more important, our variation in hole size now is plus or minus 10 nanometer. So every grid now is the same in a way that it fundamentally wasn't, that can give you consistency. And that's really the most important thing I think about these grids, as I'm going to show you, is that they're consistent in a way that traditional grids just haven't been. Okay, so there you go, just to show you what they look like. You've got 50 micrometer hexagonal squares with 300 nanometer holes. You have 9 million holes on a hexafoil compared to about 850,000 on a standard R2, R1.2, 1.3. You do have to use them at high mag, and we have introduced a bunch of fiducials to make it easier for you to see them at high magnification. When you're using them, you need to glow discharge them longer, you need to blot them much larger and longer and harder, and data collection at 165,000, if you're going to get the advantages of these high density holes, you really need to make sure your eucentric height and your image shift is absolutely spot on. It needs to be done just before you do the data collection, and then you will see great consistency. And this is just an example where if you just leave the same the same image shift correction after the last session of the microscope, you kind of miss the hole at the edge of the APHIS region because you're at 145 nanometer. But if you just recalibrate, you get most of every hole. And just to say, you can use it on glaciers, but because of the beam, if you don't have fringe-free imaging, you do have to skip, but you can use them. Okay, so I've just given myself just about enough time. There you go. If you've got a hole, you can hardly see the ice is there because it's so flat. You've got a 35 nanometer ice plus or minus 6.5 nanometers across the whole grid. So you can really use every hole on your grid. And this returns, on the left, you have hexafoil, on the right, you have ultrafoil. It means that you have very, very consistent. So the relative ice thickness here is going 1 to 1.4 compared with an ultrafoil, which is flatter than a carbon, of 0.5 to 2. So, and you can see that's reflected in the CTF and your average defocus. Somebody said to me, this almost looks like you've just drawn an array here, but I promise you it's real data. And what that pays forward into then is that your hexafoil, you get a little bit of extra resolution. This is 2.57 to 2.35, but the maps are less noisy. So you will see more features because you've got less background noise. So even though some of the sub-angstrom motion stuff isn't very relevant at mid resolutions, this less noisiness is going to make a big difference to your life, and the consistency, it makes processing and things much easier. Okay, that's just to prove that, yeah, even if somebody else does it, particle tracking is the same. You know, you go from ultrafoil where you can see motion to particle tracking, all the motion in your particles eliminated. I'm not going to go through zeros unless somebody asks me. There we go. This is my favorite quote at the moment for what's good about pleasant experience with the hexafoils. For a bit of microscope presets tuning, the grids yields crisp maps with the lowest ever B factors on the target protein. For small molecule brown structures, the hexafoils will be my go-to grids. And I just want to say thank you to everybody at Quantifoil that helped with development, everybody at SPT, of course, Chris and Katerina at the LMB, but also all the people whose data I've just shot through there that shows everybody, Peter Harrison at EBIC, Felix Weiss at IBS, Yehuda and Sebastian, people at USCD, so many people who have tested and been kind enough to share the hexafoil images and data that they've had of the early grids. Okay, and yeah, we've got a new building coming, so your lead times for everything else should get lower. Thank you very much. I think I just about managed it.
Thanks very much, Claire. I think this is super exciting. I haven't yet used hexafoil grids, but it's definitely on my list of grids to try. Maybe I'll kick off with a question while people are coming up with their own. So I was wondering, clearly the HexAuFoil grids are going to mostly address the problem of motion, right?
Yeah.
So I was wondering, are there sort of particular, in addition to that, are there particular samples, like is it better for smaller proteins versus larger proteins? Does it have a particular effect on the ice thickness as well that you don't see in other?
Okay. So what I would say, first of all, is yes, it's an effect on motion, but I would say that almost more important is this thing I said about how the grids are now more consistent, so that you get much more straightforward processing, and actually it seems to be paying forward to really, really clean maps. So it's almost, you know, if you think about, we're all looking for consistent, reproducible sample prep. Yet but the thing that we're doing the sample prep on until now has had quite significant variability, and we've eliminated that. So that's got to give you more reproducible sample prep. But yeah, at the moment, the holes are quite small. We are seeing the best. The people get most excited about it tend to be small complexes, small membrane proteins. But we have the whistle-stop tour there, the images I showed you comparing hexafoil and ultrafoil maps, you could see that was quite a large membrane protein, actually. So we have, people have used them across the spectrum.
Thank you.
Okay, thank you. Thank you for having me.
Absolutely. Well, I don't see questions at the moment, but if you want to write your questions down in the chat,
Yeah.
I think Claire will be available to answer them in the chat as well.
Yes, and I'll be around tomorrow at the main meeting. So if anybody wanted to catch me there, very welcome to ask questions there as well.